Welcome to our presentation on elliptic curve cryptography. I will first give you some information on the usage of elliptic curves. Then I'll explain what elliptic curves are and how a key exchange in TLS works if elliptic curves are used. Finally, I will give you some recommendations regarding which elliptic curves you should use to ensure strong security. Elliptic curves can be used for different purposes. They can be used for the key exchange, that is, to establish a common symmetric key between a server and a client in a TLS handshake. They can also be used for signatures and as pseudo-random number generators, or PRNGs for short. Whenever you see a cipher suite in a TLS handshake that starts with TLS_EC, this is a sign that elliptic curves are used for the key exchange. And when you see a cipher suite that contains ECDH, this means that elliptic curves are used for signatures. There are some advantages of using elliptic curve cryptography. It is fast and secure. For example, it is faster than RSA, and it uses shorter keys than other public key schemes, for example, RSA. This makes elliptic curve cryptography more practical to use. Now, what are elliptic curves? An elliptic curve is a set of points over a finite field. Even though it is called a curve, realistic curves, that is, those that are secure to use, have little to no similarity to what you might expect a curve to look like. Here you can see an example of an elliptic curve. There are different types of elliptic curves. Here we only look at the example of Weierstrass curves. These elliptic curves are defined by the following equation. y² equals x to the power of 3 plus a times x plus b modulo p for some given integers a, b and a prime p. Elliptic curves allow multiplication, such that when we multiply a point which is on an elliptic curve with a number, we receive a point that is again on the elliptic curve. Thus, given a point p on the curve E and some number x, we can calculate the point r by multiplying p with x, and the result r will also be a point on the curve. This calculation is essential for establishing a common secret between a server and a client over an insecure channel. This common secret will later be used by both as their symmetric key. The only operations that are allowed, though, are add and double, so we have to decompose the multiplication into these steps, but this is possible for all multiplications. Now let's look at how a server and a client can establish a common secret using elliptic curves, even though this communication can be eavesdropped by everyone. In an ECDH Key Exchange, where EC is short for elliptic curve and DH signifies Diffie-Hellman, we have a client and a server. The client chooses a secret number Q and calculates its public key by multiplying this number Q with a publicly known point G. This publicly known point G is also called the generator of the elliptic curve that is used, and it is a point on this elliptic curve. Similarly, the server also chooses a secret number, let's call it S, and multiplies this number with the generator G. The result of this multiplication is then the server's public key P. In order to establish the common secret key, the client now sends its public key, that is the point Q, to the server, and the server sends its own public key, the point P, to the client. Having received the public key of each other, client and server can now calculate their common secret symmetric key by multiplying the received public key with their own secret number. For example, the client has received P, which is S times G, and multiplies this point with its own secret number Q. This results in a symmetric key R, which is again another point on the curve. To summarize, the secret information that has now been established is the secret number Q, which is only known to the client, and the secret number S, which is only known to the server. Additionally, the secret symmetric key R, which is Q times S times G, is known to both client and server. As public information, we have Q and P, which are points on the elliptic curve. These points Q and P are the client's and the server's public keys, respectively. Additionally, the generator G is known publicly, which is a point on the elliptic curve, as well as the parameters A and B and a prime P that define the elliptic curve, as can be seen here. Now we come to our recommendations for you. For this construction to be secure, one has to follow certain rules. First, the point that is used as a generator G has to be a point on the elliptic curve. Be sure to also check that it is really a point on the elliptic curve. Second, it is important to use curves with a high order, that is 256 bits or more. The order of a curve can be calculated by starting with the point P and then always adding the point P again and again to itself as often as needed until the result is again the original point P. The number of additions that is necessary for this is the order of the elliptic curve. If this order is too small, an adversary can brute force the secret number of the client or the server and thus obtain the secret key. Therefore, it is very important to use curves with a high order. To avoid using curves with an order that is too small, it is recommended to use predefined standard curves. For example, there are elliptic curves defined by the NIST, for example, SecP 256R1, by the BSI, that are the brain pool curves, or curve 25519, which was designed by Bernstein. The problem with generating your own curves or implementing standard curves on your own is that it is very easy to make a mistake, which renders the complete crypto insecure when you use your curve or your own implementation of a standard curve. Typical problems with non-standard curves or implementations are too few points on the curves, performance issues, or the leakage of secret information, for example because of a timing side channel. So please stick to the standards when using elliptic curve cryptography. If you want to learn more about TLS and TLS security, then please visit our TLS Academy website.